Good day. This is a follow-up to the last video. We're going to look at graphs of equilibrium. We're going to look at changes in concentration. And we're going to look at these changes in response to things like stresses. We're not worrying about it too much quantitatively. The quantitative part will happen when we do the math of equilibrium. But right now this is more descriptive and I want you to start to get a handle of what these graphs look like. You'll see that I chopped out sections from your textbook, and I've given you the page number if you want to see things in more detail. So here we have CCl4 plus 2 HFs becomes CCl2 F2 plus 2 HCl's. But the CCl4 is in a liquid state, and that means we don't have to worry about it in terms of our equilibrium. Liquids have fixed concentration. So that's why only three things are plotted. These three chemicals, the HF and the two products. Now we can see that the first part of this graph is showing that the product started at 0 and the HF started up here, whatever number that is. As we went to equilibrium, the HF has to drop. And the CCl2F2 and the H2HCl's, these materials increase. Well, this dropped, the HF dropped by the same amount the HCl went up because 2 to 2, remember stoic from last year. This is a coefficient of 1 in front, so it came up half as much. So we've done all that to get to equilibrium. These things have flattened out. This vertical dotted line represents the time of a stress. That stress was an increase in concentration. Increase in concentration of the HF. Le Chatelier's principle says, if the concentration reactant goes up, the stress is going to shift to the right to use up some of the reactant. So now we see it dips a bit. So it dips a bit. The HCl comes up by the same amount, 2 to 2, and the CCl2F2 comes up by half the amount because of a 1 to 2 ratio. Now we're at a new equilibrium. So the first thing to notice is when it's a concentration, is a change in concentration is a stress, only one material is going to spike or drop at the time of that stress. The second thing to realize is these values may be different than what they were, but everything has gone up, and when we put it into our KEQ expression, it will give us the exact same KEQ value. The next stress we're going to look at is pressure, and I don't have a tidy way of moving, so I'm going to do it this way. And we should arrive on page 2. Okay. Now page 2 shows a pressure stress, different equilibrium. Here we have 2SO2 plus O2 becomes 2SO3. Pressure, change in pressure only affects equilibrium that have gases, and this has gases, so now we have to deal with it. We can see we arrived at equilibrium by having SO2 and O2 reacting. The SO2 dropped by twice the amount of the O2, and the SO3 came up, and we're at equilibrium. When we do a pressure stress, all of the concentrations are going to increase. And in fact, this graph isn't exactly perfect because the higher up, it's going to have the greater concentration change. But what we care about is how does it respond to that stress? Well, we know it's increase in pressure by decreasing the volume because all of the concentrations went up. We're seeing a spike, spike, and spike. On this side, we have 2 moles of gas in the products, 3 moles of gas on the reactant side, according to coefficients. 2 and 1 is 3, and there's our 2. More pressure, because of smaller volume, that shifts to the right. So the SO2 keeps going up, and the SO3 keeps going up, and the SO2 and the O2 both drop. And we arrive at a new equilibrium, and if we plug it into a KEQ expression, it will have the same value of KEQ before the stress was applied. So the two things to get from this graph are, when we have a pressure change, all three things will increase or decrease at the time of stress, and there's no change in KEQ as we arrive at a new value. We got to go to our third stress. So let's go to page 3. All right. Here is our temperature stress. We've arrived at equilibrium with the SO2 and the O2 reacting. The SO3 came up in concentration. So at this time we're at equilibrium and we impose a stress. Now it said the stress was a decrease in temperature. And we are told that this decrease in temperature leads to an increase in the SO2. And we know decrease in temperature favor the exothermic reaction. So energy would be over here. We have a negative delta H. So by decreasing the temperature, we get more SO3 produced, and the SO2 and the O2 drop. But now these both are lower. This is higher. It no longer satisfies the earlier value for KEQ. So at a new temperature, we have a new value of KEQ. So in a temperature change, everything curves to a new equilibrium. There's no spiking or dropping of any of the chemicals. It's a curving to a new equilibrium and they flatten out again. We're going to go to our last page of notes here. Let's go to 4. Boom, boom, boom. And now we're looking at an equilibrium related to smog. So we have NO2 and N2O4. And this one involves pressure changes. So when we increase the pressure by making a smaller volume, you can see we've compressed it. Initially it goes darker. And it goes darker because we've made the concentration of everything higher. We've taken this, whatever moles of gas, and we've completely compressed it. But over time, it gets lighter. And what it means is we're going from the darker NO2 to the less dark, the clear N2O4. Because if we increase the pressure, it favors the side with fewer moles of gas. And the N2O4 only has 1 mole of gas, one coefficient of 1, whereas the NO2 had a coefficient of 2. So that describes it. This is also in your book, and we love to ask questions about smog and things about whether it's endothermic, exothermic, and all that fun. But that's your introduction to graphs. Doesn't make sense? Watch it again or ask me questions.